Okay, more problems. Woo! Yay! Because the more problems that we practice on, the more confident we get. And the more we find mistakes that we're making, which gives us a chance to correct mistakes. Because, when we're taking the real exam, our goal is no mistakes. No mistakes. And that's where we're moving towards. All right, well, practice is how we get there. Let's get going. First problem. Solve, there's a lot of stuff here. So there's this expression, x squared minus e to the x minus y plus 3y squared times y prime. Plus 2xy plus e to the x minus y, 8x, 3x squared plus 5 to the 1/3 equals 0, with y of 1 equals 1. Now, when you look at this, you might say, oh my God, hopeless, right? Hopeless. There's all these things mixed together. And normally, if you see something like this, you're like, is there anything that we can do? Well, this is a good time to say, maybe it's exact. You see, if it's exact, there's a nice tool that we have that lets us solve it. Now, what do we mean? Well, exactness says that really what's going on is that in some sense, this whole expression is a derivative of a single function. And if we can just figure out what that function is, then we're done. So how do we do it? Okay, so the setup, so just recall that when we're talking about exact, we're really going to talk about something in the form m dy plus n dx equals 0. You might say, we're out already. There's no dy or dx. Well, that's okay. We can fix that. You see this y prime, another way to think about y prime is to think of it as dy over dx. Now, when we say dy over dx, you might say, like there's something called dy and there's something called dx. Technically, dy over dx is one thing. It's not two things. But let's pretend like it was two things, and let's see what we would have. So, if we imagine multiplying through by dx, we can say, okay, then this is x squared minus e to the power x minus y plus 3y squared dy plus, and the other part, 2xy plus e to the x minus y plus 8x, 3x squared plus 5 to the 1/3 dx equals 0. Now there's some tests for exactness. Now if you suspect something is exact, you can actually test really early to see if it is exact, and that involves comparing what we call partial derivatives. So one way to do it is to say, well, take the partial derivative of what's in front of the dy with respect to x. And if you do that, you get 2x minus e to the x minus y. And here, take the partial derivative of what's in front of the dx, take that with respect to y. You get 2x plus minus e to the x minus y. And we're like, whoa, they match. Perfect, exact. Now that's one test. I'm not going to do that. Well, two reasons. One, I don't like that test. In some sense, when you have problems like this, it's a redundant test. But the other thing is, we're not actually required to test for exactness. We just have to find it. So we will point out along the way, and here's another reason that we know it's exact. So how does the process work? Well, the basic idea says we're looking for one function, and in essence, we have some pieces of it, at least we have derivatives of it. Now, it's a function of two variables, so when we talk about we have pieces of it, that means we have really two partial derivatives. So here's what we do. We say, okay, let's integrate m dy and see what that would be. So we're integrating our x squared minus e to the x minus y plus 3y squared dy. Now, when you integrate with respect to dy, that means anytime that you see an x, you treat it like a constant. So the integral of x squared, well, x squared is a constant. So you think about 5, what's the integral of 5? 5y. So the integral, the first term, is x squared y. Now the integral of the second term, that x upstairs is a constant. Okay, so we integrate, there's that minus y up there. And so when you integrate, well, it'll be minus e to the x minus y. But then we say, okay, we got to compensate for that minus sign in front of the y, divide by -1, which turns this into a plus. And the integral of 3y squared with respect to y is y cubed. Wonderful. And then a constant. A constant what? Well, it's not a constant number because it's a constant with respect to y. And anything which only depends on x is a constant. So some constant function of x. All right, great. Well, that's part of it. Now, the other part, if you like the other perspective, we integrate n dx. Okay, so we integrate 2xy plus e to the x minus y plus 8x times 3x squared plus 5 to the 1/3 dx. And we're integrating with respect to x, so y is a constant, but the integral of 2x, okay, that would be x squared y. The integral of e to the x minus y, well, the minus y is acting like a constant. So think of it as like e to the x. Well, that's an easy integral. It's e to the x minus y. And then there's that other part. 8x, 3x squared plus 5 to the 1/3. What? How do you integrate that? Well, let's just focus on that one piece. Now, that function, as it's currently written, is not part of our table. That's okay, that often happens. We know how to handle that. The main tool, and that should be your first thing you think about, is there like an easy substitution that makes things nice? Substitution is probably the most powerful tool when you talk about integrating functions. And it's your go-to thing to do. Now in this case, when you think of substitution, you say, all right, look for something on the inside. Substitution is an inside job. So there's a candidate here. So we're going to let u be the inside. 3x squared plus 5. Then du would be 6x dx. Well, we can move the 6 over. So we could say 1/6 du is x dx. Now, just this piece, what happens? Well, the 8 is 8. And then the x dx is 1/6 du. And the 3x squared plus 5 to the 1/3 is u to the 1/3. All right, well, now, well, that's great. We know how to integrate that. That's not bad at all. Now, 8 and 6 have common factor 2. So you'd say, well, that's 4/3. And then you would add 1 to the exponent. So 1/3 plus 1 is 4/3. Then multiply by the reciprocal would be 3/4. And it's like it was meant to happen. Or if you will, it's like it was planned to happen that, hey, things simplify nicely. So we really get u to the 4/3. Now there's a plus c floating around. I'll go ahead and put, there's some constant here. And so, but finally, you put back what is u, 3x squared plus 5 to the 4/3 plus some constant. Okay, so back to our regularly scheduled problem. And we have that the integral of the last piece is 3x squared plus 5 to the 4/3 plus, now what goes here, a function of y. Again, it's a constant with respect to the integral that we're doing. Now is our time. This is where I would say, hey, let's test for exactness. And here's the test. You compare the pieces that have both x and y in the function. And you say, okay, the overlap, in other words, things with both x and y match, and that's all you need. And so we say, aha, so this is exact. Good. And now we're basically done. So here's what we need to do. We need to piece it together, and the way we piece it together is we take the overlap part. Okay, so that's going to give us our x squared y plus e to the x minus y, and then anything that didn't fall in the overlap. So there's a y cubed, and there's a 3x squared plus 5 to the 4 thirds. Okay, now, is this the answer? No, definitely not. There's a couple things wrong here. One thing is, we should have something equal something. So this should be equal to something. And what should it be equal to? Well, some constant. And okay, so there's a constant we haven't used yet. Now are we done? No. Okay, what? Well, we are in essence, we've done the hard part. We said, look, this is the right answer. So we're able to piece together, say, okay, this is the right function. And when I say it's the right function, what we're really saying is that if you take the derivative of this left-hand side, this big expression, you actually get that. On the other hand, if you take the derivative of the right-hand side, you get 0. So great, they match. The thing that we have to do, of course, is our initial conditions. Now, we say that y of 1 equals 1. So really what that says, okay, we plug in, namely x equals 1, y equals 1. That's our initial condition, and that lets us solve for f. So we're going to get 1 squared times 1, which is 1. E to the 1 minus 1, it's e to the 0. Well, e to the 0 is 1. 1 cubed is 1. I'm picking a theme here. All right. Whoops. Why did I put 3x to the 5th? My goodness. I was getting ahead of myself. 3x squared. All right. Now, 3 plus 5, 8. Cubed root of 8, 2. 2 to the 4th. Well, that's 2, 4, 8, 16. So, 1 plus 1 plus 1 plus 16 equals f, or f is 19. And now we just write down our answer. Basically, we just have to replace f by 19. And you'll notice this happens a lot. As you start to do these problems, you're like, you know, it's not so bad, the problems. You just get to copy a lot. Well, when you get to copying a lot, you tend to make some small copy errors. You know, like I accidentally copied a 5 instead of a 2. You know, that's natural to make small copy errors, and especially if you're rushed. And so what you don't want to do is you don't want to rush. Take your time. Enjoy the problem. And the other thing is just sort of like scan, say, oh, wait a second, that doesn't seem right. And you're like, oh, yeah, it's not right. And catch your mistakes early. The sooner you catch your mistakes, the better. You know, because oftentimes mistakes have a way of snowballing, right? And so let's stop that. Let's stop that early in the process. All right, one problem down. That's a nice warm-up. Number 2. Oh, an essay problem. Well, let's see. A colony of robots start on a small planet and then continuously build a larger planet. So you can think of it, they start in this small sort of little tiny small planet. So here's our initial small tiny planet. But then what happens is they keep building out, right? You know, because robots, they can just, you know, they're not constrained like we are. And so they keep building and make a bigger and bigger planet. It essentially becomes a planet of robots. Now, there's this next sentence. Consequently, the population corresponds with volume, right? Okay, so the volume is measurement of how many robots there are. That seems reasonable. While rate of growth is proportional to surface area. Well, again, that makes sense because, you know, where can the robots move? Well, the only way they can move is on the surface. You know, otherwise it's all packed. So the only place they have to grow is on the surface. Okay, great. That seems reasonable. It is also the case that the robots slow down construction over time. We all slow down as we get older. You know, I've noticed that, you know. If you watch my videos, I definitely go slow because I'm getting older. That's okay. You know, there's ways to help cope with that. All right. So the model that describes the population growth of this planet, of this robotic planet, oh, good. We don't have to drive it. They gave it to us. P prime is 5 e to the minus t, p to the 2/3, where p is the current population in millions and t is measured in centuries. Given that initially there are 1 million robots, P of 0 equals 1, find P of t. Also determine the number of robots there will be as t goes to infinity. All right. Now, if you're like, oh man, there's a lot to digest here, notice that we can actually write this problem with just the following. P prime equals the differential equation. And the reason you might say, well, why is there a p to the 2/3? That's how you go from volume to surface area. There's that sort of correspondence there. So that's sort of the 2/3. And P of 0 equals 1, find P of t. And that's basically the problem. It's like all of this is just sort of beautiful extra flavoring that helps us enjoy it. And then, of course, there's a second part of the problem. So you really should think of there's two phases to this problem. And the second part of the problem is, okay, what happens to P of t as t goes to infinity? So once you understand that oftentimes a lot of the text is just descriptions, you say, oh, what's the essence? You're like, oh, that's not so bad at all. Because it's not. It's not bad. So how do we go about solving this? Well, we start P prime, or if you like, dp dt, population. There's lots of models for population. Now the e to the minus t, that's what says, hey, our rate of growth slows down with time. So as t increases, that causes the p prime to slow down. So that's the rate of growth slows down with time. And we already talked about p to the 2/3. We're like, well, wow, this is a nice differential equation. In fact, we see everything's multiplying together. And usually when you see lots of stuff multiplying together, that should be a clue. Think separable. And separable works really well here. All right, so that says dp divided by p to the 2/3 is equal to 5 e to the minus t dt. So that's step 1 of a separable differential equation. Step 2, after you've separated the two sides, you integrate the two sides. Okay, now how do you integrate this side? Well, one way to do it is to say, hey, this is actually the same as the integral of p to the minus 2/3 dp. And that's the more calculus way to write it. Now you might say, why do you use calculus way? Well, when we're dealing with exponentials, we really like to have it as p to the something. So we don't like the square root symbol. That doesn't really mesh well. So we say, oh, square root symbol becomes like to the 1/2. And things downstairs become to the negative exponent. So what's the integral? Well, you add 1 to the exponent. Minus 2/3 plus 1 makes a 1/3. And now divide by 1/3, same as multiply by 3. Integral of 5 e to the minus t is minus 5 e to the minus t. And this minus in front comes because of that minus there. You actually have to divide by the coefficient. In this case, divide by minus 1, same as multiply by minus 1. And you need a plus c. You only need one. You don't need to put a plus c on both sides, just one side. All right, great. So that's using our differential equation, the fact that it's separable. Now we pull out a p of 0 equals 1. Okay, so we get 3 times 1 to the 1/3. 1 to any power is 1, is equal to negative 5 e to the 0, 1, plus c, or we say c is 8. And so now we know c, so we say, okay, well, moving up, that says p to the 1/3 is equal to, well, we can write it as 8 minus 5 e to the minus t over 3, because we have to divide both sides by 3, or we come to the conclusion that p, and the way we get rid of the 1/3 is cube. So p is equal to 8 minus 5 e to the minus t over 3 to the 3rd power. All right, so that's part of our answer. Good. Now, there's that second part. What's the number of robots approaching? Now, I'll never get there. That's the whole point about infinity. It's not that it gets there, it's that it approaches. So what do we approach? What's the answer? Well, in this case, we say, look, as t goes to infinity, let's think about what happens. Well, the only place t is showing up is at e to the minus t. And the exponential function, if you plot the exponential function, it's going down as you head off towards infinity. It's at e to the minus t, right? Now, I got to be careful because there's the e to the minus t versus e to the t. So, all right. So the point here is e to the minus t goes to 0. And so we get that p is going to approach 8 over 3 cubed. And you might say, that's not a very big number, but remember, the population is in millions. So, yeah, it's not a small number. There's many, many millions. Plenty of other robots for the robots to hang out with. All right, well, that's fun. Well, these are fun problems. Yeah, aren't they? Sometimes we get distracted and we lose track of things and we forget, hey, math is meant to solve fun problems. All right. Now, the next one. Find a solution to y triple prime plus 3y double prime plus 2y prime plus y is equal to 14x e to the x minus 3 e to the minus x. Now, there's a really wonderful, beautiful word that when we see it in the context of this problem, we're like, oh, we love you. And they even highlighted it for us. It's this word right here, a solution, one solution. So we don't have to find a general solution. We don't have to find a solution with some initial conditions. We just have to find one solution. So what's that really telling us? Well, it's telling us that it says, hey, we need to find a particular solution. So, in essence here, we have a problem where it's solving a non-homogeneous problem and finding a particular solution for that. All right. Now we have tools for this. And, of course, there's very complex tools, which involves variation of parameters. But, unfortunately, variation of parameters we can't use because, well, for many reasons. But the first thing we can't use it for is this is a third order differential equation. We haven't talked about the machinery for variation of parameters for anything above a second order. So, okay, that's out. Great. Well, now we know we're not doing that. But there's other reasons, which we'll see in a few moments. Okay, so our mindset is now, if it's not variation of parameters, it's non-homogeneous. And we should have said, okay, it's non-homogeneous because, well, you have this part over here. That's telling us it's non-homogeneous. We're doing method of undetermined coefficients. So here's the basic idea. We come to this and we say, all right, we look at our pieces that currently are on our right-hand side, and there's two pieces, x, e to the x, e to the minus x. We say, all right, great. So we have x, e to the x, e to the minus x, and these are our parts that we're going to be putting together. And now there's three rules that we have to remember. One is, if you have a power in front, you have to have all lower powers. Notice we have an x, e to the x. Well, that means we have to have an e to the x. All right, e to the minus x, that's good to go. All right, sines and cosines come in pairs. No problem here. There's nothing sine and cosine at all. And now check for overlap with the homogeneous. And we're like, okay, great. So now we're going to solve the homogeneous differential equation. Okay, or are we? Spoiler alert, we're not. But we just have to do enough. So if we look at the homogeneous, we have r cubed plus 3r squared plus 2r plus 1 equals 0. You're like, oh, well, that looks hard. Can you factor it? Well, in theory, yes. In practice, maybe. It depends. And in fact, one of the things that we can test, there's this beautiful rule that says if it does factor nicely, the roots, the possible nice roots, you can figure out by looking at what's in front of the leading power and what's in front of the constant. Well, since they're both 1s, it says the only nice roots are 1 or minus 1. Okay, so notice if you plug in r equals 1, you get 1 plus 3 plus 2 plus 1. You get 7. Well, that doesn't equal 0. So 1 is not a root. All right, well, that's not good. Well, if you plug in negative 1, well, you get minus 1 plus 3 minus 2 plus 1. Well, that gives 1. And, well, 1 is not 0. So that says negative 1 is not a root. And you're like, uh-oh. So there's no nice roots. So we're not going to be able to factor this in a nice way. And at this point, you might be starting to like, oh, what do we do? What do we do? But actually, we've done all that we need to do. You're like, what? Wait, we have? So what do we need? So what we need to do is make sure that there's no overlap from the parts that we're putting together with the homogeneous solution. So you don't actually have to have the whole homogeneous solution, you just have to have enough to say, oh, there's no overlap. Now, if there was overlap, that would have to say either 1 is a root, give us e to the x, or negative 1 is a root to give us e to the negative x. So these two pieces of information tell us that e to the x and e to the negative x are not solutions to the homogeneous. And that says, great, no overlap, and so we don't need anything else. We don't need to know what the homogeneous solution is because we're not finding a general solution. We're just finding a particular solution. And so great. So now we've got our parts. So we're ready to begin. Our particular solution that we're after looks like some combination of these pieces. So A, x, e to the x, b, e to the x, c, e to the negative x. And now what we do is we take our derivatives. So we're going to take first, second, and third derivatives. So we just have to be patient here. Now, if you take the derivative of x times e to the x, product rule, right? So the derivative of x is 1 times e to the x plus x times the derivative of e to the x, which is e to the x. And so if you work it out, you'll get x plus 1 e to the x. Derivative of e to the x is e to the x. Derivative of e to the negative x is minus e to the negative x. Yp double prime. All right. Well, product rule again. Well, derivative of x plus 1 is 1. So you have 1 e to the x, and then x plus 1 times derivative of x is e to the x. So 1 plus x plus 1 makes it x plus 2. All right. Well, that's great. Derivative of e to the x, e to the x. Derivative of e to the negative x, well, negative comes down again. All right, pretty predictable. The third derivative, because we do have to go all the way to the third derivative. Okay, can you see the pattern here? X plus 1, x plus 2. I think you can probably guess. Yeah, it's x plus 3. Now y, derivative of the first would be 1 times e to the x, then x plus 2 times derivative of e to the x is e to the x. So at every stage here, if it's times e to the x, you just add. All right, derivative of e to the x still e to the x. Derivative of e to the minus x, the minus comes down again. Okay, so the point of all this, the punchline, well, we have that 14x e to the x minus 3e to the minus x is equal to, well, yp triple prime plus 3 yp double prime plus 2 yp prime plus yp. In other words, I'm just plugging the particular solution in. And now we take these expressions and put them in. All right, so there's a lot of copying here. So just be patient. A, and so this is our triple prime. So copying b e to the x minus c e to the minus x plus 3. Okay, now copy double prime. A x plus 2 e to the x plus b e to the x minus c e to the minus x, okay, plus 2. Now copy the prime. A x plus 1 e to the x plus b e to the x minus c e to the minus x, and now copy the function. So nothing so bad, just a lot of copying. Well, it's not the first time we've encountered problems that involve lots of copying. So now to gather. Okay, so let's see. X e to the x. What do we have? Well, we have an a from the first one, 3a from the second one, a 2a from the third one, and an a from the last one. All right, so those are all the x e to the x terms. Now, the e to the x, this one's going to be fun. Notice that there's 3a plus b. That's the first one. Here, we're going to get 2a, but don't forget there's a 3, so that makes it 6a and 3b. That's the second one. Here we'll get 2a and b. So 2a and b, and then just b. All right, so there we go. There's our e to the x terms. And our e to the minus x, well, nothing too bad. We have minus c from the first one, minus 3c, and hold on, let me check. Yeah, 2a. Oops, I forgot. There should be a 2b. Why? How could I forget the 2b one? The classic to be or not to be question. Yeah, something was seeming off because I was like, am I forgetting the 2 there? And the answer was, yes, Steve, you were. All right, great. Well, now we fix that. All right, now the other thing I noticed is I copied wrong. So that should be a plus. All right, see? Something felt wrong. Minus. Wait, no, that doesn't seem right. It should be alternating. See, that's why it helps to pay attention when you're doing things. You might be thinking, wow, that seems like you're just making it up as you go along. Well, not entirely. Hopefully not. All right. Well, now we clean it up. A, 3a, 2a, a. That would make it 7a. And that has to equal the coefficient. So in other words, it has to equal this coefficient on the other side. So it equals 14. Over here, we're going to get 3a and 6a and 2a. So that would make a total of 11a. And then we're going to get b and 3b and 2b and b. So 4, 6, 7. So 7b. And that equals the coefficient of e to the x over there. What is it, 1? So that equals 0. All right. How about here? Minus c plus 3c minus 2c plus c gives us c. And that has to equal coefficient of e to the minus x, negative 3. So what do we see? All right. Well, great. We see that a equals 2. That's pretty straightforward. We see c equals negative 3. Again, that's pretty straightforward. And now, well, a equals 2. That's 22. Move it across, divide. B would be minus 22 over 7. All right, well, good, good. Now, what do? Well, we have our coefficients for A, B, C, and we know our particular solution has that form. So the last thing to do is just write in those values. So we have that our particular solution is equal to 2x e to the x minus 22 over 7 e to the x and minus 3 e to the minus x. And that's it. We're done. Wow! Woohoo! It worked out. And it wasn't so bad. On a side note, 22/7, some people like to use that as an approximation to pi. It's okay. They're better. They're a better approximation. That has nothing to do with the problem. They're just like, wow, 22/7. Hey, cool. Okay, so no big surprises. In some sense, this idea of like, oh, we don't have to do the whole homogeneous solution. Well, if we just want only the particular solution, we really just have to say, is there any overlap? That's what we really needed. So now we know. Now we know. And knowing, as they say, is a significant part of the battle. Maybe even half. Okay. All right. All right. Number 4. Find the solution to x prime, which is 1, 1, 4, 1, x, with x of 0 is 110. Okay, well, okay, we kind of know what we have to do. This is straightforward, no hidden strings. It's just saying, we have this system, solve it. And hey, don't forget, we're going to throw you some initial conditions. Make sure you solve those as well. All right, great. And so I would say, for this, we should start by doing eigenvalue method. So how do you start eigenvalue method? Well, we have our matrix A. All right. So we're going to take 0 and set equal to the determinant of A minus lambda I. All right, so that's the determinant. 1 minus lambda, 1, 4, 1 minus lambda, which is 1 minus lambda squared. Subtract 4 times 1 is 4. Well, that would be 1 minus 2 lambda plus lambda squared minus 4. Well, okay, that's really lambda squared minus 2 lambda minus 3. Now, does that factor? And if so, how? Well, it does. So lambda minus 3, lambda plus 1. You can always check, right? Lambda squared, that's good. Plus lambda minus 3 lambda is minus 2 lambda. And minus 3 times 1 is minus 3. All right, so this is actually a nice scenario. Our eigenvalues are, first off, nice numbers. Good for us. High five. And the other nice thing, of course, there's no repeated roots. They're distinct. They're real. And so that says we're going to succeed in finding eigenvectors. We're guaranteed. No surprises are coming our way. So we are going to do next, the next thing, well, we have our eigenvalues are positive 3 and negative 1, because remember, we want this to equal 0. So at positive 3, negative 1. We want to find the corresponding eigenvectors. Okay, so there's going to be an eigenvector for 3, and there's going to be an eigenvector for negative 1. All right, so let's do these, and it's actually not so hard. So the idea here is to focus on A minus lambda I, and we have the general form. We just plug in the right value for lambda. So suppose we want to do lambda equals 3. So we're going to do our A minus lambda I. So just everywhere you see lambda, put a 3. So minus 2, 1, 4, and minus 2. And now we're going to multiply it by some vector AB and set this equal to 0, 0. We just need to find a choice that does this. We don't have to find all of them. We will, but we just need to find one. And if you think about what's going on here, you have a system of 2 equations and 2 unknowns. minus 2a plus b equals 0, and 4a minus 2b equals 0. But of course, as must happen, there's redundancy. So we can get rid of 1. Say, oh, that really says b has to equal 2a. So our vector, AB, really looks like a 2a. Or, if you pull an a out, 1, 2. So our eigenvector for 3 is 1, 2. Now the thing is, you can always check eigenvectors. Take your eigenvector, multiply it by your original matrix. So if you did, you'd have 1 plus 2 is 3. 3 times the first entry. 4 plus 2 is 6. 3 times the second entry. And so we see that we scale by 3 when we multiply, which means we definitely got the right eigenvector. All right, well, do it again, -1. So come back, here's our a minus lambda I we can refer to. And when we put in lambda equals -1, we get plus 2, 1, 4, plus 2. And again, similar setup. And we can see, hey, there's 2 equations that we're solving for. But wait a second. What? It's the same equation. We knew that. Come on. Come on, come on. No need to be silly. And, well, okay, so that says b looks like -2a. So our AB is really a minus 2a, which is a 1 minus 2. So there we go, 1 minus 2. All right. And again, as we did, if we wanted to, we could check, hey, yeah, 1 subtract 2 is -1. That's like scaling the first integer by -1. And then we have 4 subtract 2 is positive 2, which is scaling -2 by -1. Now, why do we do all this? Well, the reason we do all this is because we know that we can make good solutions. In fact, we have the following. Once we have eigenvalues, eigenvectors, we get solutions. And the way we get it is it's e to the eigenvalue times your time times your eigenvector. And e to the eigenvalue times your time of your variable, eigenvector. So we found our 2 solutions. And once we have those 2 solutions, we say, oh, well, that's really all the solutions, because we can stitch them all together. There's that notion of superposition. So we now have that x looks like some constant a times e to the 3t 1, 2, plus some constant b e to the minus t 1 minus 2. And what we have to do is solve for a and b, and that's where our initial conditions come in. So x of 0 is 110. And the nice thing is e to the 0 is always 1. So we get a times 1, 2, plus b, 1, -2. And if you read off the equations here, a plus b equals 1. Right, that's just reading off the first top entry. 2a minus 2b equals 10. Well, okay, that's the same as saying a plus b equals 1, a minus b equals 5. And this is like, well, just add them together. Okay, yeah, sure. If we add them together, what happens? Well, 2a equals 6. So that says a has to equal 3. And now 3 plus b equals 1, because I'm just coming up to the first equation, plugging in a equals 3. So that says b equals -2. So now we know a and b, and therefore we know the answer. We just put in what are a and b, and so our solution looks like the following. 3 e to the 3t 1, 2 minus 2 e to the minus t 1, minus 2. And there we go. A beautiful answer. Beautiful answer. Now, if you wanted to, I'm not saying you have to, but if you wanted to, you could put it all together. So another way you could write it is to say, oh, this is the same as x equals, and then it would be 3e to the 3t minus 2e to the minus t, and then 6e to the 3t, and minus 2 makes plus 4e to the minus t. Both are very nice answers, and it's just a matter of how do you like it. I personally like this because it really emphasizes. I look at that and say, I see all the parts. I see your thought process, and I know you did it right. Good job on you. All right, great. Well, that's problem 4. We're halfway there. Woohoo! Unfortunately, it's probably the second half that might be a little bit longer. But, you know, we don't know until we try. So let's try. Number 5. Find e to the at, for a is 8, 9, negative 4, negative 4, and use this to solve x prime equals ax with x of 0 equals 1, 2. All right. Now, when you're looking for e to the at, there's a couple ways to do it. Almost always you want to start by finding eigenvalues, because one of the things you can do, okay, so let me just back up a step. One way you can approach this is to say, hey, start with x prime equals ax and find the solutions to that. Once you have the solutions, you can make a fundamental matrix. Once you have a fundamental matrix, you can augment and turn it into e to the at. So that's the phi of t times phi of 0 inverse. And so that's sort of a process. It starts by saying, let's look at the eigenvalues. All right, so here we go. Set 0 equal the determinant of a minus lambda I, which is equal to 8 minus lambda, 9 minus 4 minus 4 minus lambda. Okay, so that's going to be 8 minus lambda times minus 4 minus lambda, subtract negative 4 times 9. Minus lambda times minus lambda is lambda squared. Then we're going to have a minus 8 lambda plus 4 lambda. So minus 8 plus 4 makes minus 4. Minus 4 lambda. All right, and then the next is minus 32 plus 36 makes plus 4, which is lambda minus 2 squared. Wow! Wow! Repeated eigenvalues! This is awesome! This is so awesome! Okay, now you're probably like, whoa, Steve, calm down! Oh, why are you getting so excited about repeated eigenvalues? Let me tell you something. It turns out if you have repeated eigenvalues, now you don't have to take my word for it because we're going to do it 2 ways, but I'm just going to show you something that's really cool. All right, so if you have a 2 by 2 matrix and the eigenvalues are the same, so lambda, lambda. Okay? Then it's always the case that e to the at is equal to e to the lambda t times the identity matrix 1, 0, 0, 1 plus t times the matrix a minus lambda I. That's the whole thing. Now, what does that say for us? Well, lambda equals 2. So we would have e to the 2t times 1, 0, 0, 1 plus t. Now, what is a minus lambda I? Well, okay, so it's this matrix. We'll plug in lambda equals 2. 8 minus 2, 6. And then we have 9. And minus 4. Minus 4 minus 2 is minus 6. And if we just clean that up, we can multiply the e to the 2t through. We can put those together. We get the following. We get 1 plus 6t e to the 2t, 9t e to the 2t. Then we'll get 0 e to the 2t, and then t minus 4. Okay, so that's minus 4t e to the 2t. And the last part is we'll get e to the 2t, and then there's this minus 6t, so it becomes 1 minus 6t e to the 2t. And we're done with the e, solving for e to the at. That was quick. That was like super quick. And you might be saying, that was too quick. Is that right? So we're going to do it round 2. So if you don't want to memorize this, or you're just like, I like taking time on these problems. I want to enjoy myself. A shortcut? Ugh. Who wants to do a shortcut? All right, great. Well, let's do it a little slightly longer, but also valid way. Okay, so we know we've got lambda equals 2, and it's a repeated eigenvalue. We also can see that this is an interesting matrix, which means if it's a 2 by 2 repeated eigenvalue, you're going to be short eigenvectors. So we're going into the problem with the mindset, hey, we're short an eigenvector. So what do? Well, we start with a minus lambda I, which we already found down here. But again, we can just plug in lambda equals 2. So we have our 6, 9, minus 4, minus 6, times our vector AB equals 0, 0. So this is our step 1. We're really finding our eigenvector. Well, okay, so this is 6a plus 9b equals 0, and minus 4a minus 6b equals 0. Now, they may not look the same initially, but the longer you stare, you say, oh, if you divide the top by 3, that's 2a plus 3b equals 0. If you divide the bottom by minus 2, it's 2a plus 3b equals 0. It's really the same equation. So we cancel one of them out. And like I said, you could divide. So we say, oh, okay, so that's like 2a plus 3b equals 0. And we just need to find a solution that works. And so we say, oh, okay. Well, we can pick, let's pick a to be 3. So then we'd need b to be negative 2. So it's one of those like, oh, hey, sort of like change the coefficients. But if they're both on the same side, you have to flip the signs on one of them. Now, why do we like this 3, negative 2? Well, we like it because this is an eigenvector. So that's good news for us. We found the eigenvector. But now we have to get ready for the bump, because there's bumping involved in this problem. Okay, so we're going to repeat a computation here. Well, not really fully repeat, but it's going to be similar. Moving our way through the alphabet, CD equals what we just found, 3, negative 2. So we get a system of equations. 6c plus 9d equals 3, and minus 4c minus 6d equals negative 2. But again, it's really the same equation. There's redundancy. So, all right, let's pick the top one. We can, again, divide by 3. Well, that's good news for us. So 2c plus 3d equals 1. And now we just need any solution that works. Now there's a lot of things we could do. We could pick a half for c and 0 for d, 0 for c, a third for d. You can, if you hate fractions, avoid fractions as well. So for example, if I choose d equals 3 and c equals negative 1, well, that does it. And there are infinitely many answers. So don't be like, oh, I didn't get the exact same answer Steve got. Does that mean I did it wrong here? No. It just means Steve has a fraction phobia. And so he was like, let me find a way to do it so I can make these numbers work where I get whole numbers the whole time. All right, so -1, 1. Now this is something else. It's not an eigenvector. That's important. This is what you might call that generalized eigenvector. So keep that in mind. And all right, well, great. How does that help us? Well, now what we have is we've really built up the components to say what a solutions look like. So we have two solutions. So our solutions, we can say, look, x equals some constant. I'll use capital A. And then we use the eigenvector. So it's e to the eigenvalue t, eigenvector. And then plus b, e to the eigenvalue t. And now the bump. Well, you have t times eigenvector plus this little extra piece. Okay, so that's what we have. Now, what comes next? Well, remember, our goal is to find e to the at. And so now we construct phi. So phi of t, well, what we do is we populate it with solutions. So this first solution will become the first column. So we're going to have 3 e to the 2t and minus 2 e to the 2t. And then the second solution is going to become the second column. So you have to sort of squish it all together. And if you do this, you get 3t minus 1 e to the 2t and minus 2t plus 1 e to the 2t. All right, so there's our phi of t, our two solutions. Are we done? No? Because they don't match yet. But they will, because the next thing we do is to say, all right, what is phi of 0? Well, phi of 0, plug in e to the 0, those become 1s. Anything with the t's becomes 0s. So we get 3 minus 2 minus 1 plus 1. Okay, what's phi of 0 inverse? And the answer is, well, 1 over the determinant, 3 minus 2. Well, that's good news. That's a nice determinant. Nice. You swap the order on the diagonal. So these change places and change the signs in those two off diagonals. Now, as always, you can always check your answer by carrying out multiplication. 3 minus 2, 1. 3 minus 3 is 0. Minus 2 plus 2 is 0. Minus 2 plus 3 is 1. Okay, so there's our phi 0 inverse. Now, the key here is we're going to take this matrix and we're going to put it right there and carry out a multiplication. Because what we know is that e to the at is phi of t times phi 0 inverse. All right, so here's the computation. Okay, be patient here. We get 3e to the 2t plus 2 times this. All right, so 3e to the 2t and then plus 6t minus 2 e to the 2t. All right, so boom, boom. And then minus 2 e to the 2t plus 3 times. Okay, so that would be plus minus 6t plus 3 e to the 2t. I hope I can fit this all in. Okay, boom, boom. All right, going down. We have minus 2 e to the 2t, and then plus minus 4t plus 2 e to the 2t. And last, minus 2. Right? Wait, hold on. I feel like I've done something wrong here. Bum, bum. Oh, yeah. This minus 2 should be a plus 3. Yeah. Yep, I did it wrong. All right, let's fix that. So it's 3 e to the 2t, 9t minus 3. Good. So, okay, now fixing it. I really found that entry. Whew. All right, see, that's the danger here. You got to work it out carefully. Minus 2 e to the 2t, and here we're going to get plus minus 6t plus 3 e to the 2t. All right, which is 3 and 6t minus 2 is the same as 1 plus 6t e to the 2t power. 3 e to the 2t, and then we have minus 3 e to the 2t cancel, so we're left with that 9t e to the 2t. Down here, minus 2 e to the 2t, and then there's going to be a plus 2 e to the 2t, cancels, and what's left? Well, that minus 4t times e to the 2t. Here you have a minus 2 e to the 2t and a plus 3. Well, that becomes a plus 1, and then minus 6t, and that's times e to the 2t. And there we go. Now, catch our breath. Do they match? They do. Both techniques are valid. And you're probably thinking, okay, so I can either do this or that. Yes. Yes, you can. Yes, you can. All right. Wonderful. Are we done? Almost. One last part. Remember, we have to solve with some initial conditions. But once you have e to the at, that's basically a freebie from that point on. So the last step, and put it in the upper right corner here. So we're going to have our e to the at times our initial conditions. So whenever you have the e to the at matrix and you have initial conditions, it's super easy. So, well, we just copy. Well, we'll copy from here. Okay, so 1 plus 6t times e to the 2t minus 4t e to the 2t, 9t, careful here, I don't want to run off the page, e to the 2t, and 1 minus 6t e to the 2t, times 1, 2. All right, so here we go. So one of these and two of those. Okay, so we have 1 plus 6t plus 18t. Well, that's quite a lot there. Well, what does it become? It becomes a grand total of 1 plus 6 plus 18 is 24t e to the 2t power. And now we have one of these and two of those. Okay, so, well, we'll have 2 and minus 4t minus 12t. Minus 4 minus 12 minus 16. So minus 16t e to the 2t. And done. That's it. What a fun problem! And, all right. Well, we did it in two different ways. Well, we did the hard part in two different ways. So, good. Well, that one's done. All right. That's brings us to number 6. And you know what that means? It's Laplace transform time! Ah! Which means we have our table. So make sure you have your table ready to go, because we might want to refer to it as we do these problems. Part A. Find the Laplace transform of 4t squared e to the 3t times u, that unit step function, 2t minus 3. All right, that doesn't seem so bad, and nothing too surprising, t squared e to the 3t. But if you look at it, there's something a little bit unusual about this problem. Notice something here. If we look on the inside, we see 2t minus 3. Now, we're really used to the unit step function. It's sort of a very nice intuitive function, right? You know, it's one day you're off, and the next day you're on, right? So it's 0 and 1. You know, off, then on. And the key thing is, okay, how do we know? How do we know if we're off or if we're on? And we look and we say, okay, we look on the inside. Now, if we saw u 2t minus 3, where would we think we turn on? What point do we transition? Now, the logical thing is we're so used to seeing, you know, the unit step function in a certain way. We say, oh, it's at 3, right? Right? Maybe, but maybe not. The 2 changes things. So the fact that there's a 2 there means like, let's pay attention. So, you know, don't let, how do I phrase this nicely? Don't get too used to like tradition, you know, because we know how people think. Your instructors, they've been working with students for years and years. They know how you think, and they know how to get you, because they're like, oh, we know your comfort zones, so we know how to take you just outside your comfort zones when you're not paying attention. All right, so let's think about it. Let's think about what's going on here. All right, well, sort of the key thing here is to think about, when do we transition? Now, when we think about the normal unit step function, well, the transition happens at the inside is 0. So we say, okay, so we need to say, when does 2t minus 3 cross 0? Now, that's not a bad question. We can actually answer that one pretty easily. So we say, oh, well, 2t minus 3 will equal 0 at time t equals 3/2. So what that means is that the unit step function of 2t minus 3 is the same as the unit step function of t minus 3/2. Because they both have the same place where they're 0 at the same time, they're negative at the same time, they're positive at the same time. So I say, all right, great, good. So that makes our life a lot easier. So we say, okay, so our real problem is we're looking at how do we rewrite 4t squared e to the 3t u of t minus 3/2. Now for this, whenever we see a u something involved, we go back to our table, right? And we look at it, and we say, aha, there's one key part of the table. Now, f t minus a u t minus a. That's where we're going to be queuing. That's the place where we say, hey, that guides us. So if we have a t minus 3/2 here, we need to rewrite this piece in the form of t minus 3/2. So all the work of this problem, well, not all of it, but the bulk of the work of this problem is sort of a pre-processing type thing where we're going to rewrite our expression so everything looks like t minus 3/2 involved. And once we get through that, well, then the rest of it's pretty quick. So, but there's a lot of preparatory work. So, you know, we got to do the work. But once we finish, it's not so bad. So how do we get there? Well, the key idea, and we'll write it down for reference here. So the key idea is to say, you know, t is the same as t minus 3/2 plus 3/2, right? Because if I, you know, subtract 3/2 plus 3/2, I get 0. And so there's a way to rewrite t in terms of t minus 3/2. All right, so we're just going to do that. All right, so this is really 4 times, well, t minus 3/2 plus 3/2 quantity squared, e to the 3, and then we'll have some parentheses here. Parentheses are really important. They're good friends. parentheses help save points. And so it's always good to get into the practice of using them. All right. Now, well, let's expand a little bit. So here we square things. All right, so we have the 4. Then it's t minus 3/2 squared. And then there's the cross terms, right? So it's like a squared. Then the middle term is 2ab. So it's 2 times this times that. Well, 2 times 3/2 will give us 3 times t minus 3/2. And we do want to keep t minus 3/2 as t minus 3/2 for now. We like that. Like, we really, really like that. So we're not going to touch that. And then, of course, there's 3/2 squared. Makes that 9/4. Now here, if we multiply the 3 through, that's e to the power, or 3 times t minus 3/2. And times what? Well, 3 times 3/2 is 9/2. Okay, so 9/2. And then we have our u of t minus 3/2. Okay, so let's put the 4 in. 4 times 9/4, that's pretty nice. And now we should note, of course, make another quick note here, e to the 3t minus 3/2 plus 9/2 is equal to e to the 3t minus 3/2 times e to the 9/2. In other words, we can separate addition into multiplication. It's one of the nice rules about exponents. And you might say, God, that's so old, Steve. That's like algebra. Do we need to know it? Yes. Yes, you do. You should know algebra. It's a very useful tool. A lot of what we do really is just algebra with a few extra steps involved. All right, so we're going to clean it up. Okay, so we have the following. Well, there's this e to the 9/2 times everything. Okay, great. Just e to the 9/2 times whatever we're going to get out at the end. Then we're going to have t times, don't forget the 4. 4 times t minus 3/2 quantity squared e to the 3 times t minus 3/2. And then plus 12 t minus 3/2 e to the 3 times t minus 3/2. All right, and plus 9 e to the 3 times t minus 3/2. And all of this is times by the unit step function of t minus 3/2. Okay, we've done our pre-processing. And the good news is that's the hard part. Now, of course, that doesn't mean it's the only part, but it's an important part. Now, we go through and we talk about each piece, what's happening here. Well, so the big thing is we've rewritten this part in terms of t minus a. So it's all t minus 3/2. Now, that says we're going to have an e to the minus as. So that says there's going to be an e to the minus 3/2 s. So we're not going to forget that. But now, what about these individual pieces? Well, don't worry about the t minus 3/2. Think of it as t. So what about e to the 3t? Well, we have e to the at. It's 1 over s minus a. So if it's e to the 3t, then this part right here would become 1 over s minus 3. What about te to the 3t? Again, the 3/2 is just the shift. Well, that's on here as well. So we would have that this part would normally go to 1 over s minus 3 squared. And t minus 3/2 squared e to the 3 t minus 3/2. Well, again, don't worry about the 3/2. It's really like t squared e to the 3t. So we can use this rule. N equals 2, a equals 3. So it'd be 2 factorial, which is 2, over s minus 3 cubed. All right. So we have 2 over s minus 3 cubed. All right, now we're ready. We're ready. We've done our work with our pre-processing. So what does this go to? Well, it goes to the following. We have our e to the 9/2, which is our constant. And constants just do what constants normally do. And then we say, okay, what happens to the inside? Well, we have 4 times 2, which is our 8 over s minus 3 cubed. And then 12 times 1 over s minus 3 squared. And 9 times 1 over s minus 3. And then when we do this, we'll get e to the minus as times that. So minus 3/2 s. And the other thing we can do now is say, hey, these are both exponents. We can put them together. All right. So if we do that, we get an answer of, well, the 8 over s minus 3 cubed plus 12 over s minus 3 squared plus 9 over s minus 3 times e to the 9/2 minus 3/2 s. And there we go. Not so bad. You see what happened here? What happened on this problem? If we do a quick review, right? A lot of it was we said, oh, we have to do this sort of prepping, pre-processing, where we take our expression and we expand it out so that everything is phrased in terms of t minus 3/2. And, we use our basic rules in algebra. And once we had that, we say, okay, great. So this was our f of t minus a. So, what was f of t? Like, well, 4t squared e to the 3t, 12t e to the 3t, 9e to t. Like, okay, we can process those. And so that's what we get times, e minus as. But we have that little extra piece, and so we put it all together. There we go. Not so bad. Yeah, of course not. It's not bad at all. All right, well, that's part A. Wonderful. We're done. Don't have a lot of room left. And we still have part B. So time for us to get some more paper. Now, the good news, as always, paper grows on trees, and so there's plenty of paper out there. So we'll just put that there. And so we're ready to start part B. Okay, so we're after the inverse Laplace transform of this. And notice it's a straightforward polynomial over polynomial. This is all about the partial fractions. And so, great. So that's our mindset going into this problem. All about partial fractions. So the first thing we should think of doing is factoring the denominator. So once we understand it's partial fractions, we don't have to pull off like, there's like an exponential term, pull it off to the side. No, nothing like that. Okay, so the upstairs is what it is. Don't do any factoring upstairs. It's counterproductive. It's the downstairs where you have to factor. Okay, and you might be like, oh, quartic, fourth degree polynomial. Then like, oh, wait a second. It's really a quadratic, right? I think it was like s squared squared. So suppose I asked you something like, suppose I said t squared plus 5t plus 4. You're like, oh, I can factor that. That's t plus 4, t plus 1. Like, oh, yeah, same thing, except now it's t is s squared. So this is s squared plus 1 and s squared plus 4. All right, well, we write it in our right form, so you have something over s squared plus 1 and something over s squared plus 4. Well, they're both irreducible quadratics, so we're going to end up with as plus b, cs plus d. 4 variables to solve for. All right, well, off we go. Now, the first thing to do, clear your denominators. And when we do that, we get to the following. You can do 8s cubed plus 6s squared plus 17s is equal to as plus b times s squared plus 4 plus cs plus d times s squared plus 1. And now you're like, aha, pick good values. And you might say, man, are there no good values? Well, it depends on how comfortable you feel with complex numbers. If you're okay with complex numbers, then what you can do is you can substitute I or 2I. And when you do that, the other thing to keep in mind is that all the answers for A, B, C, and D are real. And if you go through and carry out the computation, the answers pop out pretty quick. But let's suppose we are not comfortable with complex numbers. I suspect that applies to a couple people. So what now? There aren't any good choices. So what we do is expand. Okay, so this is A s cubed plus b s squared plus 4as plus 4b. Over here we have cs cubed plus ds squared, and then we have plus c times s plus d. Or, if you like, that's s cubed a plus c plus s squared b plus d plus s times 4a plus c plus 4b plus d. And now compare coefficients. And we're just start comparing. Well, the s cubed says a plus c needs to equal 8. S squared, b plus d has to equal 6. 4a plus c, that has to equal 17. That's a big number. And 4b plus d, oh wait, that's the constant term. There is no constant term. So that equals 0. And, well, now you just start chipping away. Now, it might look like, oh, there's 4 unknowns, there's 4 equations, but actually, they split nicely into 2 sets of unknowns and equations. So, we have the following. We can say, okay, we need a plus c to equal 8, and at the same time we need 4a plus c to equal 17. All right, well, imagine you multiply the first one by a minus, and you add the two together. Well, 4a minus a is 3a. The c's cancel, and 17 subtract 8 is 9. All right, that says a equals 3. And now you say, oh, if a equals 3, 3 plus c equals 8, and so therefore c equals 5. Okay, so now we know a and c. On the other hand, we say, look, b plus d, that has to equal 6. 4 times b plus d, that has to equal 0. Well, now, again, imagine you subtract the first one from the second one. 4b minus b is 3b, and these cancel, and 0 minus 6 is negative 6. Say, oh, okay, well that says, hey, b has to be negative 2. All right, well, if you come up here, negative 2 plus d equals 6. All right, that says d has to equal 8. And now we have b and d. Wonderful. Wonderful. So, we are now to here. So our expression as plus b over s squared plus 1, cs plus d over s squared plus 4 becomes the following. And let me pause and say, take this part and don't try to rush it. Make sure the numbers go in the right places. So, a goes here, so that's 3 times s plus b, so that's minus 2 over s squared plus 1, and c times s, so c is 5, so 5 times s plus d plus 8 over s squared plus 4. Now at this point, we're thinking sine and cosine. Insofar as if you look at sine and cosine, they have the right form, s squared plus a squared downstairs. So if it's an s upstairs, we're happy. If it's a constant, we want the constant to be a. So we'll clean it up just a little bit more, just a slight smidgen more. So we're going to break it up. So think of it as 3s over s squared plus 1. And then when we have s squared plus 1 with a constant, our preferred constant is 1. So minus 2 times 1 over s squared plus 1. Then, okay, 5 times s over s squared plus 4. And then our constant, preferred constant would be 2, because a is 2. And we have 8, so we'll have it as 4 times 2 over s squared plus 4. And, of course, each one of these pieces fits our table. S over s squared plus 1 is cosine. 1 over s squared plus 1 is sine. S over s squared plus 4, cosine 2t. 2 over s squared plus 4, sine of 2t. All right, good. I'm just looking at my table to make sure, because it's easy to confuse sine and cosine. They're so close to each other. So close to each other, sometimes without meaning to, you swap the rules. And, if you have a table, don't be a hero. Use the table. It's okay to check. You don't have to be like, aha, I'm so confident, I'm not even going to look at the table. No, it's okay to look. It's totally okay. No one will judge you. So our answer, 3 cosine t minus 2 times sine of t plus 5 cosine 2t plus 4 sine of 2t. And we're done. All right, good. So we found our Laplace transform of one function, our inverse Laplace transform of another. Okay, that finishes up number 6. So we're turning our corner. 2 problems left to go. And our next problem is number 7. Use Laplace transforms to solve y prime plus 2y equals f of t, with y of z equals 0, and where f of t is the function shown below. I was like, what? They didn't give us a literal expression. It's not even a piecewise. It's not like here's f of t equals this. It's just like, there's a picture. Here's f. Okay, great. That is f. So now we've got to figure out what's going on. So f of t, it's up, down, level, right? That's the picture. Up, down, doom. Okay, so what do you do? Well, some pieces are pretty clear. From 2 onwards, we're 0. Okay, so that's not too bad. Now, the first part is also pretty clear. Okay, so initially, what happens? Well, initially, we start at 0. It's a line segment, and we're going up. And what's our slope? Over 1, up 4 means our slope is 4. So this is the line 4t. So, okay, that's 4t. And then we have that other piece. And the other piece is not bad, but we got to, work it out. Okay, so what's that last little piece going to do from 1 to 2? Well, we can see the slope, right? It's down 4 over 1. So negative 4 over 1. Negative 4 is our slope. What's our intercept? Well, you could imagine if you kept going, it would go up another 4. So it would normally the intersection, y-intersection would be at 8. And so this segment is 8 minus 2t. So there we go. So we can take the picture and say, okay, if that's our graph, here's the behavior for each piece as a function. We're going to go one step further and say, all right, well, so what does that tell us? We're going to write our function in one-line notation. It's initially 4t. So you start with what is it initially, and then we say, we've changed behavior at time 1, so we have a flip. We turn off the 4t. We turn, what? Why did I say 8 minus 2t? I tell you, I would, can't believe how many times I make copy errors, you know? And it's okay to make copy errors. Just catch them, right? Yeah, catch your copy errors. Okay, so we turn off the 4t, that's why you subtract it. Turn on the 8 minus 4t. All right, great. And now, the other thing is we say, okay, u of t minus 2, because we switch behaviors at 2. And we say, all right, turn off the 8 minus 4t. And then what? Turn on 0. Okay, so there's f of t in our sort of one-line notation using our step functions. Now, as we always like to do, we want to clean up our functions. So if it's u of t minus a, the piece attached to it looks like t minus a. So let's see if we can do that here. This part, that's the same as 8 minus 8t, right? Because I can put the minus 8t's together. Or the same as minus 8 times t minus 1. Now that's nice. It's really nice, actually. Beautiful. Now how about here? Well, this is really the same thing as 4t minus 8, which is the same as 4 times t minus 2. And so we're like, hey, this is actually going to turn out to be pretty nice. So our function f of t that we're going to use is 4t minus 8, and we can put it as t minus 1, u of t minus 1, plus 4 t minus 2, u t minus 2. All right, great. Now we're ready to go. And notice we only have a first-order differential equation. That's right, you can use Laplace transforms to solve first-order differential equations. That's still perfectly fine. In some sense, Laplace transforms work really well when you have some function f of t that is piecewise. Because if you didn't have Laplace transforms, what you'd have to end up doing is say, okay, let me solve the differential equation from 0 to 1. Okay, now how about from 1 to 2? Okay, how about from 2 on? And you're like, okay, chipping my way through. Whereas here, it's just like, oh, we'll just do it all at once. Isn't that kind of cool? It's just like, we don't have to break it up. We'll do it all, we'll do it, you know, as they say, we'll do it live. We'll do it live. All right, great. So, now let's talk about the Laplace transform of f of t. So, Laplace transform of f of t is what? Well, Laplace transform of t, it's on our list, well, kind of. So where does it show up? It's t to the n. So Laplace transform of t is 1 over s squared. So we say, okay, so this would be 4 over s squared. And here, this t minus 1, we still treat like t because of this shift. So it's minus 8 over s squared e to the minus s. And again, this t minus 2, we're going to treat like t because it's attached to that shift. So plus 4 over s squared e to the minus 2s. All right, so that's the Laplace transform of the right-hand side. On the other hand, we have that the Laplace transform of y prime plus 2y, well, it's going to be equal to, because y of 0 equals 0, that's going to become s times capital Y of s plus 2 capital Y of s. Or if you like, that's s plus 2 capital Y of s. All right, great. So we know the Laplace transform of both sides, and so now we can solve, and we come up with the conclusion that the following is true. So we'll block this part off, that worked, and we say, all right, look, y of s is equal to 4 over s squared times s plus 2 minus 8 over s squared times s plus 2 e to the minus s plus 4 over s squared times s plus 2 times e to the minus 2s. And now you're looking like this, like, oh man, we've got so many partial fractions to work with. But actually, we don't really, because they're basically all the same. I mean, don't worry about the e to the minus 2s. See, like, these are exactly the same, and this one is just off by a factor of 2. So what we can do to help keep our sanity a little bit more reasonable, well, sanity, what? We can do the following. So let's do the partial fraction decomposition of 4 over s squared times s plus 2. All right, so that's 4, not 4, a, why am I doing lowercase a? All right. It's been a long test, right? All right, relax. No worries. Capital A over S, capital B over S squared, capital C over S plus 2. Clear the denominator. So multiply both sides by S squared times S plus 2. You'll get A times S plus 2 plus B times S plus 2 plus C times S squared. All right, so we'll pick some nice values. We can pick, say, S equals 0. That'll be nice. And we get that 4 equals 0 plus 2b plus 0. Okay, so that says b equals 2. We can also pick another nice value, would be negative 2. 0 and 0 and 4c equals 4. So 4 equals 4c. All right, great. C equals 1. All right, and now you're like, well, I'm out of nice values, but you only got to find one more number. Okay, so just pick any value for S. All right, 1. 4 equals A times 1 times 3. 3A. B times 3, so 3B. But B is 2, so 6. Plus C, which makes it plus 1. Okay, well that's 7. You can subtract, and so you get that 3a is negative 3, which says a is negative 1. All right, great. So we have the following. 4 over s squared times s plus 2 is equal to our a, so minus 1 over s, plus our b, which would be 2 over s squared, plus our c, which would be, 1 over s plus 2. All right, good. Now we're mostly out of space, and this is going to be a little bit of work. So we need a little bit more space than what we have left on the page. So we're going to go to another page. Wow! A 2-pager. In this day and age, yes. Sometimes some problems need a little bit more work. That's okay. That's all right. All right, so let's copy the key points here. So the key points are, we know what y of s is. Namely, that's 4 over s squared times s plus 2 minus 8 over s squared times s plus 2 e to the minus s plus 4 over s squared times s plus 2 e to the minus 2s. And the other thing is we've also figured out that 4 over s squared times s plus 2 was equal to, it's this part right here, minus 1 over s plus 2 over s squared, and then there was a plus 1 over s plus 2. Okay. All right, so that's what we have. I'm going to put this to the side, and we're going to continue. So our goal is we're solving the differential equation, which means we need to do the inverse Laplace transform of that. So what we're going to have happen is we're going to use this fact for each one of those three. So we have that y of s is equal to, so I'm going to do the first part, and it's just a straightforward copy, minus 1 over s, 2 over s squared, 1 over s plus 2. Now here, notice these differ by a factor of minus 2. So we can just say, okay, this is the same as plus, multiply everything by minus 2. So 2 over s minus 4 over s squared minus 2 over s plus 2 times e to the minus s. And the last part, again, we're back to just copying 1 over s minus 1 over s, 2 over s squared, 1 over s plus 2, e to the minus 2s. All right, and our sort of the last thing is to make sure we understand what all the things do. So we know e to the minus 2s, that's a shift by 2, e to the minus s, shift by 1. When we look at 1 over s, that's a 1. 2 over s squared, well, 1 over s squared would be t. Don't forget the 2. Well, okay, so I'll write 2t just so I don't forget. Make that minus 1. 1 over s plus 2 would be e to the minus 2t. Yes. Good. Because if you look at the table, again, we have the table. Why not use it? So, see, 1 over s plus 2, that's s minus minus 2. So that's why it's e to the minus 2t. All right, the rest of the terms are very similar. So, again, we'll just work our way through. So this part will be positive 2. This will become negative 4t. And this will become minus 2 e to the minus 2t. And, okay, this is our minus 1. Here's our plus 2t. And here's our e to the minus 2t. All right. Whew. Now, we're ready to write our answer. So, we get the following. Namely, y of t is equal to, all right, minus 1 plus 2t plus e to the minus 2t. Okay, so that's the initial, no surprise. And then something happens at 1. So we turn on some behavior at 1. And what's the thing that we turn on? We have 2. And then minus 4t, but we shift. So minus 4t minus 1. And then minus 2 e to the minus 2 t minus 1. Okay. Plus, we shift by 2. So we turn something on at time 2. And what do we turn on? Well, minus 1. Then there's a 2 times t minus 2. And then there's an e to the minus 2 t minus 2. All right. So that's the answer, except one small detail. We have succeeded. We have found the solution to this differential equation. But notice it says, okay, use Laplace transforms. We did. We solved this. We have. And express your answer as a piecewise function. See, right now, it's not a piecewise function. Just like, here it is in all its splendiferous glory. So how do we express it as a piecewise function? Well, we say, okay, well, where do we switch? We switch at 1. We switch at 2. All right, so we are going to say that y of t is equal to, and now we say, all right, let's start before our first switch, our initial thing. Minus 1 plus 2t plus e to the minus 2t. And this is for t less than 1. So before our first point of switching. Now, at our next point of switching, this is when things get fun. Okay, so notice this is the same as 2 minus 4t and plus 4. Okay, and the other thing is, of course, here you can think of this as minus 2 e to the positive 2t times e to the minus 2t, right? Because you can think of the minus 2 going through. Okay, so let's see what we have. So we've now switched on both pieces. So constant, we have minus 1 and 2 and 4. Put those all together, you get 5. Plus 2t minus 4t makes minus 2t. All right, good. And all right, and then what's the other part? Sorry here, I just always cautious, right? It pays to be cautious. It pays to be cautious because, you know, we don't want to make any mistakes. We've worked hard on this problem, and so we don't want to come to the end and be like, whoa, uh-oh, we got to go back and fix some things. No, we don't want that. We don't want that at all. All right, well, that's looking fine. And now we have the e to the minus 2t, but you notice what do we have? We have one of them here, and then we have a minus 2 e to the 2t. And this is for starting at time 1 and up to our next interesting point. So up to time 2. All right. Now, our next piece. Okay, so now we're going to turn on all the switches. So now we're above 2. So what do we have? Well, we have minus 1 and a plus 2t and a minus 4. And then this, whoops, ha ha ha. Ha 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 ha. I forgot to put a plus sign here. My apologies there. And the last part will be plus, why did I write e to the 2t? It's not e to the 2t, it's just e to the 2. My goodness. Okay, and this will be e to the 4, e to the minus 2t. All right. Well, what does that make? Okay, so we have minus 1 plus 2 plus 4. That gets us up to 6. And then minus 1, 5, and minus 4. Back to 1. All right. Wow. Wait, hold on. Am I adding up right? Yeah. Minus 1, minus 4 is minus 5. Minus 1 makes minus 6. Here it's plus 2 plus 4. That makes plus. Oh, actually, it all cancels. Oh, gone. Gone are the constants. Gone are the constants. Okay, that's fine. All right, how about the t's? A plus 2t, a plus 2t, a minus 4t. Gone. All right, great. That's wonderful. That's wonderful. All right, how about the e to the minus 2t's? Well, we'll have e to the minus 2t. We have 1 here. Our minus 2 e squared there. And then plus our e to the 4th. And that's for 2 less than or equal to t. All right. And done. Done. Okay. Wow. Amazing. Amazing. It worked out. Well, maybe not as clean as you would have hoped, but yeah, it works out. And there you go. There's the answer. Well, I think the hard part might just be putting the piece, writing it as a piecewise. And so if you're thinking about how do you go about doing it as piecewise again, just say, okay, just identify your transitions. Okay, so 1 and 2. And you say, all right, just go through and say, okay, before my first transition, what happens? After my first transition, what happens? After my next transition, what happens? And just sort of work your way across. And there you go. Bob's your uncle, as they say. Well, not a lot of people say that these days. It's kind of an old expression, but an oldie but a goodie. All right. I do think this was maybe one of the hardest problems on the practice test. You got to have one hard problem on a test, right? It, keeps you honest. Keeps you honest. Well, okay, that brings us to one last problem. Number 8, as always, find the first 5 terms of the series solution centered at x equals 0. In other words, through the term c to the 4th, x to the 4th, for the following differential equation. Y double prime minus 2y prime minus 2x squared y equals 0, with y of 0 equals 2 and y prime of 0 equals 6. Now, one of the things that you might notice that's a little different about this problem than we normally see is that it doesn't say, and find the recurrence relation. So we don't actually have to explicitly find the recurrence relation. We kind of will do that, but, we'll point out that, hey, if it doesn't say it, well, there's some things we can do. You probably should count on it asking for it, but I just wanted to make that comment. Well, we begin as we do all problems involving series solutions. The first couple steps are just sort of mentally, they're all the same. So we sort of just go through the process. We know our answer looks like a sum, so we write it down, sum 0 to infinity, ck x to the k, and we're going to write down y prime and y double prime as well. And so it's just a matter of working your way slowly and patiently. And after you do it often enough, you can even get to the point where as you're writing it, you can talk about other things like, wow, how about that recently Iowa State sport game? Wow, that was either incredibly exciting or so disappointing because, that sport game, what a game. All right. Anyways, whoops, I was so excited about sport game, I had a typo there. There we go. Y prime, y double prime. And now we plug these into the differential equation. And so we get the following. Y double prime, we get the sum, k equals 0 to infinity, k times k minus 1, c sub k x to the k minus 2, minus 2, sum k equals 0 to infinity, k ck x to the k minus 1, and then minus 2x squared times the sum k equals 0 to infinity, c sub k x to the k, and all that equals 0. All right, now the next few steps, once you sort of have a method in mind, are also pretty automatic. So here's what I recommend. Move the coefficients in. Now, in our examples we've been doing on these practice exams, they've always been like numbers or numbers times powers of x. If they're more interesting, like 1 minus x squared, all right, split it up. So it's like 1 times the sum, x squared times the sum. But other than that, it's just bring it in, bring it in. And you'll notice that you're going to do a lot of writing on these problems. It's all right. And there's nothing wrong with that other than, as always, as you know, you've even seen me do it, I make copy mistakes. So keep in mind, it's like, oh, let me check. And if something doesn't feel right, that's like, hey, let me go and check to make sure I didn't make a copy mistake. Because, boy, that would be embarrassing. especially if you're doing it in front of a live audience, right? Well, hopefully you've got a little bit of, quiet time. You're on the test. And, of course, the interesting part here, x squared times x to the k plus 2. Wow. Or as they say, whoa. All right, so what do we have? Well, after you've moved in your powers, the next thing is to reindex, or if you like, substitution. So in this case, L will become k plus 2. Here, L will be k minus 1. And here, L will be k minus 2. Lots of reindexing going on here. Wow, cool. This is the same as k equals L plus 2. Here, same as k is L plus 1. Here, k is L minus 2. Yeah, you betcha. You betcha. All right, so what do we have? Well, this is also a step where it's easy to make small mistakes. So remember, everything's being changed. So we're all k's, we're moving to all l's, or whatever symbol you like. There's nothing sacred about k's and l's. You just use the symbols that you're comfortable with. So initially we started at k equals 0, but notice we're going to subtract 2, and like L equals negative 2. That doesn't sound right. But the nice thing is, hey, we can actually start this at 2. The reason we can start at 2 is the first two terms are automatically 0. It's like we pulled the first two terms off. So if we do that, we say, okay, L equals 0 to infinity. All right, k becomes L plus 2, k minus 1, L plus 1, c sub L plus 2, x to the L. This will feel really familiar. You're going to have like a deja vu moment during the exam. It's like, wait, where have I seen this before? Oh yeah, it was like on all the practice. Yeah, it is. Okay, minus the sum. Now here, again, it's like, man, if I just put L, because if k equals 0, L equals negative 1, that just sounds weird. But same thought process. Hey, I can really start the sum at 1, because the term at 0 will automatically vanish because of that k. So again, I have L equals 0 to infinity. And, well, okay, so that's 2 times L plus 1. And then c sub L plus 1, x to the L power. All right, great. Now here, well, not much we can do. If we had k equals 0, L equals 2. So L equals 2 to infinity, 2 c sub L minus 2. What? Yeah. That's what it is. Yeah, that's okay. That's okay. And then it'll be x to the L. All right, and that all equals 0. Okay, so let's talk about what's going to happen here. The last thing for us to do is to put it all together into one sum. But you'll notice this starts a little bit later. So these two start at 0, and this one starts at 2. So how do we handle that? Well, the way we handle it is we don't panic. We just say, okay, no problem. So we'll start pulling stuff off the front. So let's start with 0. From the first term, we're going to get 2 times 1 times C2. So we get 2 C2. And here, minus 2 times 1 times C1. So minus 2 C1. All right. So there's no zeros from here. So again, I'm putting in L equals 0. 2 times 1 times C2. 2 times 1 times C1. Then the L equals 1 term. 3 times 2 times C1 plus 2. So that's 3 times 2 makes 6 and then C3. And here, put in L equals 1. 2 times 2 makes 4 C2. So 6C3 minus 4C2. And that's x to the 1. All right. And then we have everything else. So sum 2 to infinity of, what do we have? Well, we just gather, right? We have L plus 2 times L plus 1, C L plus 2, minus 2 times L plus 1, C L plus 1, and minus 2, C L minus 2. And that's x to the L. All that equals 0. Now, some great news. This part here, this is our recurrence relationship. Well, almost. You probably would want to clean it up a little bit. But this is where we get it. But notice we're not asked to find the recurrence relation. We don't actually have to do it. You might say, don't we? What are we asked to find? It just says find the first 5 terms. And okay, well, how do you do that if you don't solve for the recurrence? Well, the key is the recurrence relationship just gives you relationships at every step. So this is actually a relationship. And the nice thing is each one of these pieces will equal 0. So this will equal 0. This will equal 0. This whole thing here equals 0. So let's look at the coefficient for x squared. All right. So here we go. Well, actually, before we do that, let's see what we have. Y of 0 equals 2. Well, the y of 0 is C0. Y prime of 0 equals 6. Well, that really is C1. So we can start making a list. C0 equals 2. C1 equals 6. Now look here. What does this tell us? So going off our first constant coefficient, we'll work our way over here. 2C2 minus 2C1 equals 0. Well, great. Move stuff around. That says, hey, C1 better equal C2. So I know C1 equals 6. So that says C2 equals 6. Hey, we're getting close. Because remember, we only have to get up through C4. All right. So we have C3 and C4 left. All right. Now let's come to the next one. So what's our next one telling us? Our next equation tells us that 6 times C3 minus 4 times C2 equals 0. But we know C2. So we get 6 times C3, and C2 is 6, so minus 24 equals 0, so 6C3 equals 24. So that says, aha, C3 has to equal 4. We're just one coefficient away from being done with this problem. So how do we get that last coefficient? Well, think about how we got these coefficients. Our constant coefficient, our coefficient of x. So what do we look at next? Our coefficient of x squared. Yes. So that comes into here. That's put in L equals 2. So for L equals 2, we're going to get 4 times 3, which is 12, times C4, minus 2 times 3, which is minus 6, times C3, minus 2 times C0 equals 0. All right? So again, I'm gathering the coefficient for x squared. So I'm plugging in L equals 2 into that relationship. So 4 times 3 is 12, C4. 2 times 3 is 6, C3. And 2 times C0. But wait, we know stuff. C3 is 4, so minus 24. And C0 is 2, so minus 4. And that has to equal 0. All right, well, that says, hey, 12C4 equals 28. And now, well, okay, you can divide both sides by 4. And if you do that, we can say 3C4 equals 7. Or divide both sides by 3, and we come to the conclusion that C4 is 7/3. So, in some sense, these are the coefficients, and so, well, this might be an answer they're happy with. Personally, if they asked me to find the first 5 terms of the series, I would actually write out the series. So I'd say, okay, so it's 2 plus 6x, because the coefficient of C1, that's the coefficient of x, coefficient of C2 is the coefficient of x squared, coefficient of x cubed, and the coefficient of x to the 4th. And ta-da! We're done. All right, well, as always, that was a long practice, but because we slowly took our time and we really delved into the ideas, don't feel the need to rush through things on the exam. You have time to stop and think. You have time to stop and catch your errors. And you have time to do well. I believe in you. Keep studying. You'll be great. Good luck.